this analogy to deep learning, I think, should make us more humble as scientists. It should really keep our mind more open for the difficulty of the task that we are facing now in reverse engineering a system, which in a sense has a much worse history than a trained neural network.
How far along do you think that we are in understanding how brains compute? This is a very exciting time right now, but how is the cup half full? Is it half empty? How far along are we?
Yeah, I must admit, I still think no, it's pretty empty. We're doing something wrong when we model learning typically, because we take off the shelf a certain network and then we expose it to a certain learning problem then. And no network in the brain is ever in the situation then, right?
This is Brain Inspired.
Essentially, the entirety of the recent successes in AI are built on deep learning networks made of units that communicate with each other using signals that are nothing like the action potentials that underlie communication between real neurons in brains. But does that matter? How necessary are action potentials, or spikes, to manifest intelligence? It's an open question. A functionalist would say, not at all. It doesn't matter how you implement a function. What matters is the function. Deep learning folks would also likely say spikes don't matter. After all, look at all the dog breeds we can classify with deep networks that use these continuous activation functions instead of spikes. An environmentalist might think spikes are important, however, if we don't want to continue accelerating global warming and screwing up the planet for future generations by using these insanely energy-hungry continuous activation functions that deep networks use. Spikes are energy efficient, we know that, and that evolution long ago settled on spikes. Like I said, brains use them, and brains are super energy efficient. But are there other advantages spikes bring to the table? My guest today, Wolfgang Maass, has long been impressed with brains and interested in what we can learn from brains in terms of theoretical computation. He is and has been at the forefront not just of developing spiking neural networks, but of finding ways to use the experimental results in neuroscience to inspire new ways to build networks that incorporate that biological knowledge. And he doesn't understand why more folks in the theoretical computational world don't do the same. I was fortunate enough to have Wolfgang speak with me, and I had planned originally to cover a bunch of the really cool work that he's done recently on spiking neural networks and using biological findings to build in computational features in those networks. And we do talk about spiking neural networks quite a bit, actually, but we cover so much other ground, I decided, like I've done in the past, to split our conversation into 2 episodes. So in this episode, we talk more about the broad picture of the field and culture of theoretical computation and computational neuroscience, how spiking nets are growing in the neuromorphics world, some brain-computer interface discussion, and plenty more. And then in the second part, which I'll release in a few days, we go through a bunch of the features of biological brains that Wolfgang views as potential ways to inspire computational principles and build them into spiking networks. He has incorporated many of these features in his own spiking networks, and we run through a bunch of those as well. Spiking neural networks, it's such an interesting topic to me and so exciting to imagine incorporating more and more brain knowledge into AI, that spiking neural networks, will be one of the first topics that I release in the Brain Inspired course that I'm putting together. And I will include a ton of what Wolfgang has done, along with plenty other work being done as well. You can learn more about the course at braininspired.co/course. So I'm working really hard on it, and I want to get it to you as soon as I can. So thanks for your patience here. I recommend heading to the show notes, especially for this and the next episode, where I will link to a bunch of Wolfgang's beautiful and massive body of work. Those are at braininspired.co/podcast/58. Ronan, Thomas, Javier with a hard J, Ethan, Elias, Jungjun. You guys are the best! Thank you for supporting the show on Patreon. I cannot wait to share content from the course with you soon. Okay, this was a long introduction, sorry, but one last thing here. One of the things I admire about Wolfgang is his stubborn adherence to pursue what he believes is the right path to build intelligent systems. He's been doing it a long time and has faced plenty of resistance, as you'll hear, but he persists, and the work he does is all the more beautiful for it. So I wish you, dear listener, the confidence and grit it takes to do the same in your own journey, whatever journey that may be. I guess I should say also, welcome to the Brain Inspired Podcast. I'm Paul. Okay, enjoy Wolfgang. Quote, "In my darkest hour, I wonder if what we're doing is science as opposed to systematic speculation." Wolfgang, pleasure having you on. Do you know who said that?
I don't know. No.
That would be you in a talk that I recently watched.
Oh, really? Okay.
You were lamenting the theoretical computation community not taking experimental data very seriously.
Yeah.
Anyway, thanks for being on the show and welcome.
Yeah, I actually do take this thought seriously. And I must say I'm a little bit naive now. I come more from exact sciences, from mathematics, and then computer science, computation complexity theory. And then I came into or close to the field of computational neuroscience and theoretical neuroscience. And I noticed simply the way how these scientific communities work is different. My ideal of a science is physics. And I understand some of these breakthroughs in physics really came about when, particularly in the last century, there were certain experiments that didn't fit into models from Newton or other old models. And this really excited theoreticians, and they looked for a new foundation of their thinking, of their models, which would be consistent with these new experimental findings. And this, in the end, produced then theories, like quantum theory or relativity theory, which nobody would have thought about, not just sitting in their chair then, right, and thinking how the world might work.
Right.
And I think neuroscience should capture more of this process and spirit.
Well, it's interesting. It's interesting that you say neuroscience should, because, as you were speaking, I was thinking about artificial intelligence and its, beginnings, and how during its beginnings, people were wanting to understand the mind and intelligence and how it all works. And then they took some very light inspiration from the way that neurons, abstracting from the way that neurons work, and then sort of just went to town and then forgot about brains for a long time, right? But what you're saying is that neuroscience itself, or at least the theoretical side, isn't necessarily paying that as much attention to experiment as they should?
Correct, yeah. I think now, particularly in the last 10 years, when we get recordings from living animals while they act, while they learn even, and recordings from many neurons, thousands of neurons, tens of thousands of neurons, even more nowadays, you really have a rich reservoir of experimental evidence which wasn't available 20 years ago. And I think theoreticians from many areas should converge onto these data and try to make sense out of them. Because as far as I can understand them, they're really complicated, confusing. They don't fit into any simple mindset. And I think in theory neuroscience or computational neuroscience, one should really switch from an exploitation mode into an exploration mode. I personally think we probably haven't really understood the basics really of how brain circuits work, what keeps them really functional, how they learn. Then I think we're really very much influenced by ideas, partially very old ideas, from really thinking about us, over many centuries and longer. And I think this really somewhat blinds us then. I think if instead of the brain we would study the liver, we would probably make much faster progress because we don't have so many preconceived ideas how it probably should work then.
Yeah, right. One of the things that's interesting about that approach is a lot of people that I've had on the podcast, and it seems like this dominating the current zeitgeist in trying to understand intelligence has to do with Maass levels of understanding. And in particular, it seems right now the pendulum has swung to the dominant approach is to go from the higher, from top down, from the computational goals level, use that theories about that to then think about the algorithms that might be used to accomplish those computational goals, and then use those to think about how it might actually be implemented in the meat, in the hardware, like the brains and neural networks and stuff. But you're taking a different approach. So is the bottom-up approach neglected, do you think, these days? I mean, this is kind of what you're saying right now. I'm just reframing it in Maass levels, I suppose. And you've said, actually, theorists often use Maass to justify ignoring biological implementation.
Yeah, I think now I wouldn't really favor a particular bottom-up approach, but a two-pronged approach. We should keep all our wonderful ideas and hypotheses in mind, but then look at the evidence and the ground level and simply try to get those things together then. And I think partially I can imagine why it's convenient to really interpret Maass as really top-down strategies. It's so convenient for theoreticians, right? You don't have to read all these dirty papers with their funny kind of discussions about what data are right or not. You just read other theoreticians' papers, and this is much easier for you then. You don't have to get your feet wet then.
Believe me, the bottom-up people think the same way about the theory papers, at least in my own experience. So you're a friend to the theoretical community. You're a friend to neuroscientists. You are a friend to computer scientists and a friend to deep learning practitioners. You're bringing us all together around the campfire, singing the same song, perhaps. But, someone must hate you. Who despises you? What group despises you?
I don't know. I think there are many people in theory who don't like it so much if the boat is rocked then. I think the theoretical neuroscience community has some aspects of really a belief community which distinguish a community from a scientific community. So in a belief community, people cluster about certain beliefs then. And it's not encouraged to come up with completely new beliefs then. And also, if you question a certain belief, you don't become popular. And I think one sees this little bit more belief-like or church-like aspects in any conference or workshop on computational neuroscience, because people don't have any heated debates about what is the right approach then. One is just very tolerant of other people's beliefs and expects they do the same. And a little bit you keep in mind which is one aspect which doesn't occur in church. These people from this community they are likely to be editors or reviewers of your papers.
Oh, right.
And you just want to be diplomatic then, right? You don't want to make enemies. And it's the fact that there's certain dominant beliefs, like in the, say, Christian belief community. And these are people who are at top universities. They have many students. They are good friends with editors of Neuron and Nature Neuroscience. And it's not really recommendable for a generic scientist to rock the boat and to say something which goes against their kind of published beliefs and their work style. And I think this is understandable, but it would be better for the community if there would be more kind of rebellions who really say, all these theories, they don't fit with the following experiment, and I have now here an approach which is suggested by this experimental data, and let's consider this then. So I think we should rather create a community where there is a competition among many different such pursuers of their own approaches then. and where it's also easier to create new approaches which don't fit into any of these older beliefs, because characteristic for this kind of beliefs around which people group is that many of them are quite old, then several decades old. Then there are not so many really new ones. Then, and I also want to say something positive. For example, I like very much that Yuri Buzaki has earlier this year published the book "The Brain from Inside Out." And he is such a senior and respected scientist, so he doesn't have to fear for his career then. And he really questions most of the basic beliefs of theoretical and computational neuroscience. And I think now for the science at large, it would be wonderful if many also junior people would really run into this and now find really new types of models which are inspired by Buzaki's suggestions, or maybe even other alternative suggestions then. But I think just the fact that this book by Buzaki exists shows that there must be something not completely convincing in the basics of the common belief of theoretical neuroscience, or the ruling beliefs in neuroscience, because Buzaki certainly knows the literature, right? And he certainly also has his own bias, because he works on systems like the hippocampus, which is not the standard system in theoretical neuroscience. So he has a somewhat tilted or more different kind of experimental basis, but he knows the same facts as other people know, and he makes really propositions for approaches and facts which are really orthogonal to many of these common approaches in theoretical neuroscience. Then, and so this I think is really very nice, and one should see this as science, and that this is not a church community, but it has features of a scientific community.
Yeah, it's a secular community. Yeah, I really enjoyed Buzaki's Rhythms of the Brain book from many years ago, but I haven't read this one, The Brain from Inside Out. So you recommend it?
Yeah, certainly. I think this older book, Rhythms, I found it remarkable because it's really one of the very few books where somebody ventures out to go beyond their own data and speculates about how the whole brain might come together and what other problems for really brains have to face. I think in this new book, these rhythms are one of 4 or 5 different themes then, and he addresses many other aspects. And for me, I think the most stimulating proposition of his book is that the usual process in computational theory and neuroscience is that we think we first have to understand how sensory stimuli are encoded in the brain.
Right.
And he argues that this is completely wrong then. No brain would really, start to function in this way then.
Processing the incoming data isn't the first pass, huh?
No, they have to process data, but to make sense out of the data then is his point then. And his point is brains are really, their goal in organism is really to control motor action decisions, right? And so therefore his argument is that sensory input only acquires meaning in this action-oriented context then.
I love this notion. This is gaining traction over the past few years, I think, as well.
And I think he possibly really emphasizes there one particular kind of scientific habit which is very common in theoretical neuroscience, is that we all want to understand in this area how the brain works. Now let's really split this into different tasks then, right? So task A is how sensory processing works. Task 9 will be how to construct the motor output. And then I think the worst thing is then we split it not only into tasks, which is fine, but we postulate optimization goals for this individual task then. And this is then where a large part of this community really groups around and really understand this postulated goal of this sensory processing, right? And postulated goals are predictive coding and various shadings and various others, sparse coding. And in principle, this is plausible, but I find it problematic if one, as an analogy, really looks at machine learning for a moment, or deep learning, if you want to, right?
Mm-hmm.
And if you look there at a really highly tuned, highly learned, trained system and try to reverse engineering, you find it's extremely difficult.
Yeah.
It hardly ever does at any stage what you expect it to do, simply because if you optimize a whole system for a certain kind of more overriding task, it doesn't split up this overriding task in the same way as we humans are trained to do then. It simply finds whatever works best then, right?
Right.
And it has no incentive for formulating the sub-goals in any clear way then, in any theoretical tractable way then.
Yeah.
And
right.
this makes it so difficult to reverse engineer any deep learning system as far as I know then. And in that sense, I think this analogy to deep learning, I think, should make us more humble as scientists. It should really keep our mind more open for the difficulty of the task that we are facing now in reverse engineering a system, which in a sense has a much worse history than a trained neural network. Because a trained neural network is trained in the end by one author or one author group and one learning algorithm.
Yeah.
Whereas the brain was emerged from evolution. There were many kind of phases where something was optimized. Then later another optimization stage produced another system. Now they're working together then in really complicated ways. And so therefore, in this sense, since there were many different phases of development in brains which are now superimposed, then it's even harder to reverse engineer a brain compared with reverse engineering a deep learning network.
Right. Yeah, and the deep learning networks, every week there are about 30 or 40 completely different networks doing completely different optimizations on completely different problems that aren't necessarily even building on each other, although there is a lot of building on each other, but not like in evolutionary terms, like the brain has, for sure. Well, Wolfgang, you've blown up my outline here for the whole podcast, so congratulations, but I love it. So let's talk about what you do for a second. So one description of what you do, I mean, we've already gone down the road of how you approach these things, but one description of what you do is that you take a theoretical computer science approach to understanding how to compute with biological and artificial neural networks. Another description might be that you take modern deep learning and ask how to accomplish the same computation that deep networks do, how to accomplish that with the known properties of how brains function. And yet another is that you observe the computations and algorithms that brains give rise to and perform, and you model them, again, respecting their properties and constraints. Those are a little all over the place. So which is the better descriptor? How do you describe what you do?
I think this was perfect description, and I have all this parts in me then, and I find them mutually inspiring then, and also mutually encouraging, because after a long phase of speculating about the brain, it's sometimes nice simply to think about learning algorithm for spike-based hardware, and it works, right?
Yeah.
And you can measure it then. And I think one sometimes maybe gets more on an unconscious level, inspiration also for really coming up then with new ideas about the brain then.
Yeah, I think that's so valuable to sort of cycle around and always be thinking about it in very different ways, and that really they inform each other. I really think that's a great approach.
Yeah, and I think we're living in very good times then with regard to spike-based computing. Now, since not only IBM, but Intel has entered the field, and many other startup companies now are in this direction, I think this field of neuromorphic computing is changing its style then. It used to be also after Cover Meets exciting suggestions in the 80s, it used to be developed a little bit also into church-like communities where people each they love their own device, then their own small robot,
right.
Their own way of defining what cognition is then, And now this was not questioned by any common benchmarks or performance goals. Now, when these industrial giants now enter this field, then these departments they have to justify it to their managers now whether this is a viable computing alternative or learning alternative, right? And so therefore they have a much more stronger incentive to really push for benchmarking, for really getting the most out of a certain design approach then, rather than be happy with kind of pleasing paradigms, to make it really more like an engineering discipline, which I think was missing for a long time in neuromorphic engineering, because every part of engineering I know as a non-engineer, there is somewhere a theory and there are benchmarks. And both of them are missing or have been missing in neuromorphic engineering. And I think the push towards these aspects of an engineering discipline has become so much larger than, and so therefore we're seeing now within a few years much more progress in my mind than previously in the 10 years or so.
Oh, wow.
So this, I think, really provides quite a bit of insight. What I also like very much is that this, if you take a closer look at the people and also the publications from these companies like IBM and Intel, it's not really geared only towards the bottom line, in the end, creating a market and income, but they're really awed by the brain as a paradigm. Then
are they?
Yeah, they are too, certainly. I think, for example, you can simply see it, for example, just as a fact that if you look at the research groups which are funded by Intel, they have created their own network, the Intel Neuromorphic Research Community.
Yeah.
I think they're all out of 60 or now more kind of groups. And I think at least half of them are really biologically oriented. So I think there is really a strong belief also from the side of these engineers and these people at Intel that biology can teach us something.
You mean they have biology backgrounds?
No, they really they work out biological paradigms for function or other ideas for the use really of phases to structure spiking information and various ideas then. So I think this is very nice then. And I think this is somewhat less pronounced as far as I can see it at IBM, but they have in-house certainly also people who are really have more background in computational neuroscience and also bring these aspects in then.
What you come from a math background and then a complexity science background, but what drives you really? Like, well, what is your what's the question that you want to answer, and maybe even how has that changed over time?
Yeah, really intrigued by understanding how the brain computes and learns then.
Okay.
And I had approached this more or less in a straightforward manner then. So
yes, you have.
In an older times, there weren't really so many models available. You had in computation complexity theory, there were the so-called threshold circuits, which are a kind of very simplistic form of spike-based neurons. And they were intriguing complexity theory for reasons which are probably unknown outside of this community, because one suddenly found that if you put many of these threshold circuits together, even within a few layers, they suddenly gain a computation power which is really impressive.
A potential for it anyway, right?
Right. So technically it means that from the perspective of a theoretician in computer science, it could still be that with 3 layers of threshold circuits, not too many of them, you can even solve any problem which is NP, which is the class, which is all the problems one would like to solve, but cannot solve with efficient algorithms unless they belong to the subclass P then. So right. For a theoretician, this tells that already with 3 levels of threshold gates, it becomes impossible to rule out that something can be done by these circuits. They still look like such a simple model then, so that one should think now in the afternoon you could say they certainly couldn't solve the traveling salesman problem or something like this then. And this has intrigued now theoreticians now for almost 3 decades then, and they still now are struggling with this then. So now this now kind of now depth 3 threshold circuits are really a stumbling block also just from the theoretical perspective then. So one would be now very liberal and now is happy with jumping to analogies. Now it could be that evolution also at some point found now if you have neurons that even now having few layers of them now suddenly give you really almost unlimited power, and so then the problem becomes really now just to train these circuits for particular functions then. And now just one last word. Now, compared with other concepts in computer science, now I think more standard is there to compute. Now you look at gates which compute a Boolean AND or an OR or negation, and one knows if one looks at small or shallow circuits of this type, they have very limited computational power. So there's something magic happening if you replace a gate function which computes an AND or an OR, also of many bits, by a threshold circuit, which takes a weighted sum or just the majority of input bits and compares them with the threshold then. So this is really exciting now that there is a strong computational power then really emerges then just from this basic operation of then any simple neural model also, right, where you compare membrane potential with a firing threshold.
Yeah. That is kind of how the original McCulloch-Pitts neuron model worked, though, correct? So, I mean, it's a threshold model.
Right.
And we've since gotten... So spiking neural networks are a little different, but, we've since gotten away from that model. Well, we'll get to it. How about... We'll build up to it in a second. But just thinking about your background and how your thinking has, evolved. So you got your PhD in mathematics. Was it pure math? At that point, was it pure mathematics that you liked, or was it something that math could do? And I'm asking because I've asked plenty of guests, what's the most important thing for people to learn to get into neuroscience and AI? And they almost always say math or, some sort of quantitative approach, right? And so that's why I'm wondering, if you, and I think, well, starting off in just pure math, it would help to have a goal in mind. It always helps to have a goal in mind when learning a subject, and math is no exception, I think. So I'm wondering what your early goal was, like or was it just pure mathematics, the beauty of mathematics?
Yeah, that's a very nice question. Yeah. So actually, it was for me a problem as a student. I discovered that mathematics, especially pure mathematics, is something I can easily do, but I was really missing a meaning and a goal then. And the area where I wrote my PhD on was an area of a wonderful professor, Kurt Schütte, who was actually one of the last PhD students of David Hilbert, one of these really founding giants of all of mathematics. And he worked actually on Hilbert's program, on part of Hilbert's program, because what had really bothered these mathematicians in the last century was that mathematics, which has a reputation of being the most secure and safest science, has problems in its foundations then. Possibly you even can do a locally correct proof and ending up proving something inconsistent like 0 = 1, or that there's certain axioms where you don't really know whether you should believe in them or not then.
Right.
And so this I found wonderful, that pure mathematics, somewhat analogies to physics, came into a stage where it questions and it examines its own foundations then.
Yeah. And
there was this area of proof theory, which was founded by David Hilbert, which argue, let's simply look now at mathematical proofs as mathematical objects and try to understand the combinatorics of these mathematical objects, whether you can rule out that with correct proofs you can produce stupid outputs then. And so this was a wonderful program, and this is what excited me as a PhD student then. And in the meantime, it turned out there are also scientific reasons why this approach may not really bring us that much as a true answer then. But it has this feature a little bit like also theory of neuroscience, right? It's not just a kind of analytical theory, but it has a meaning or a goal which goes beyond this formalism then.
Yeah. Well, I mean, and I don't know, part of that is just luck as well, because you're, like you said, you're adept at math. And if one goes into math, something like math, all of a sudden you can apply it to anything you want to apply it to. So it's very fortunate if you can muster the desire to go down a road like that, and you're good at it. I think it's one of the most fortunate things because you can apply it to anything like you do these days. So, well, I'm glad that you did. So, okay, so I was listening to Terry Sinofsky on another podcast. I've actually had him on Brain Inspired here, but I was listening to, he was on one of the many popular AI podcasts. And I was surprised. He was talking about spiking neural networks, among other things. And I was surprised just how little the host seemed to know about brains. So if you take a deep learning course online, there are all these online courses, they always start off with, here is a neuron. It has an axon. It has dendrites. And neural nets are like a bunch of these neurons connected. And then they, I always roll my eyes and, it's like a necessary thing that they have to go through, show you a picture of a neuron, talk about a neuron, and then they go on to talk about neural networks. But it's just striking to me how little knowledge about brains people have who work with deep nets often. But the people who developed AI from the start were interested in how brains work. In fact, like the earliest modern computers that we have, the von Neumann architecture, were inspired by the McCulloch-Pitts neuron, which were inspired by how brains work. So it is interesting how neglected brains are in the deep learning world. But you interact with computer scientists and theorists and neuroscientists and deep learning folks. Where do you see room for the most contribution that's lacking now? I mean, is it really that theorists need more neuroscience knowledge? I know that you've already said that you're bringing the data to bear on it, that's really important, the experimental data. But do theorists need more neuroscience knowledge, or do neuroscientists need more theory to drive their experiments? Where's the most contribution going to take place?
Yeah, I would see this simply. I think what is needed then, and is actually fortunately happening already to some extent, that these two communities come closer together, that they inform each other. Now they pose puzzles for the other ones. And you may have noticed that in the last few NIPSs or NeurIPS conferences, there were again workshops which were combined people from deep learning and neuroscience then. And I think it's a growing field. In one of the review papers, there was even a plot which showed an exponential growth in papers which have a neuroscience content and also using or mentioning deep learning then.
Yeah.
So I think communities are growing together. And also there, I think one should really avoid to fall into kind of simple characterization then, because if you look at closer at some of the people who work, for example, at Google DeepMind in London, you find that there are many who are really extremely competent for work on the brain, right? They have even top neuroscientists like Matthew Botvinnik or Chris Summerfield from Oxford University and others. And they have top young researchers like Tim Lillicrap, who really know a lot of neuroscience but still do what people would call deep learning or AI then.
Yeah.
So I think one should avoid kind of a cartoon-like characterization of what the others are doing then. And I think one of the most common cartoons that one finds not only in computational neuroscience but also in neuromorphic engineering is that there are this kind of brain-oriented research, and there are these deep learning people who do some funny numerical game, but they don't really relate to us then.
Right.
And I think this is really unfortunate for the people who have these beliefs, but because they are to a large extent wrong then. Not only do many people who work in these companies, not only Google DeepMind, but there's also Google Brain then in the US then, another department with hundreds of top researchers, where people really have neuroscientists on board, cognitive scientists on board, they care about brains. But also deep learning nowadays is not that people think all the time about backprop or backprop through time. What you really see instead, it's a a culture of characterizing learning and architectures. When you look at a generic paper, said NeurIPS, even if they are in the end about deep learning, you hardly ever see the word deep learning mentioned. Somewhere there, deep buried in the paper, you find there's a loss function defined then. And then it's taken for granted that you have an algorithm which optimizes this loss function. So therefore, I see it this way, that deep learning is really used like multiplication is used by people who do arithmetic. You don't write papers about multiplication, you write papers about arithmetic, about number theory. You use multiplication, right?
Yeah.
And this is really what's happening. This enormously flexible uses of deep learning in ever new architectures, ever new functional contexts. This is really, I think, which makes machine learning or deep learning as a field at the moment really exciting.
But there's also there's the use of deep learning, but there's also the theory of deep learning, which gets us back to theory of computation and brains as well. And in that respect, if there's a theory of multiplication, then you would talk about multiplication in your paper, right?
Yeah. But I think at least at NIPS one doesn't find too much. There's a little bit work now from people more in other communities than machine learning who want to explain why deep learning works or sometimes doesn't work.
Yeah.
And there's a certain characteristic feature of these papers. These are people who want to prove something, right? And so this is fun, and this is just what they have learned. And then typically they have to make simplifications to the neural network model, like often assume everything is linear or so.
Right.
And then they prove something, and then this shows limitations then, right?
Sure.
And so this is a problem, I think, at the moment that I don't see really that the theory of deep learning of this type really contributes so much to understanding the power and uses and potential of deep learning then. And at the same time, I still do also concede that it's at the moment a little bit like a miracle, which really asks for scientific scrutiny, that deep learning works so well suddenly, right? Now, since 30 years ago, it didn't work so well then. And I think the more fruitful approach, and which maybe also be the most inspirational one for neuroscientists who want to peak in the field really, is in the direction of reverse engineering deep learning results then. And so this is something which was to some extent also really cultivated by neuroscientists like James DiCarlo from MIT, and now Yamins, his former postdoc now at Stanford, who really then both do deep learning experiments and they do recordings of monkeys that are trained to recognize images, and they compare kind of neural codes in quotation marks in their deep learning models and what they measure, say, in area IT then, and they find some exciting links between both, right?
Yeah.
And in the last 2 years, they have taken this even further. They started out with feed-forward networks, the standard architecture in deep learning, but now they have started to tackle recurrently connected networks. And they ask a question, well, we know from feed-forward networks in deep learning that these are really very powerful. What else can recurrent connections give us from the function level? And so this is really an exciting question for neuroscientists, because we know recurrent connections is one of the most characteristic properties of neural networks in the brain, right? And I think, in this way, one has a new approach of really approaching this question, what are they good for, right? What is the architecture of neural networks in the brain really good for?
Right.
And what I like also about this style of this work starting with this paper from DiCarlo 5 or so years ago in PNAS, is that they introduced a new style in this kind of computational neuroscience research, which I like very much because it goes very much against this trend of a church-like community. They really provided empirical basis for judging which of these models is more functional than other ones from various perspectives. And they spent a lot of time really on establishing sound criteria, for example, defining something which they call a brain score, which scores whether a model has some brain-like features then. And they like this very neutral engineering-like approach towards understanding complex architectures and possibly even brain-like architectures. And I think this will probably help us a lot.
And the fact that the networks are trained to perform the tasks, right? And so you train the network to perform the task and then look at how the units are activated and such. So, guys, by the way, Wolfgang doesn't listen to podcasts, nor the radio, I found out. But he doesn't know. You just name dropped 4 or 5 people who have been on the podcast before, so that makes me feel great. So that's friends of the show essentially. So we're on the right track here. So in some sense, we do know a lot about brains. We know how neurons function pretty well, and we have for a while. We have a pretty good sense of brain architecture, or the connectomic work is still ongoing, and so on. How far along do you think that we are in understanding how brains compute? This is a very exciting time right now, but how is the cup half full? Is it half empty? How far along are we?
Yeah, I must admit, I still think it's pretty empty. So if you take a closer look, for example, at just one basic question, neuroscience question, looking at the anatomy of a cortical column, whatever this is then, but simply a small patch of circuitry. There are many papers out there, many published models, but if you take a closer look, they extrapolate very few data then. We don't really have the empirical ground truth of really knowing which neuron, if a particular type of neuron, a particular layer, what is the connection probability to another type of neuron on another layer then. And there are, in principle, approaches for doing this, like from the Lichtman lab at Harvard.
Right.
But they didn't have the chance to get it funded, to really bring it to really use their very demanding technology to analyze a full cortical column. So it's only a tiny segment. And so therefore, in some sense, we're missing the ground truth, right? So if one believes that in a cortical column, there's a certain local circuit template, which is then stitched together to form a carpet, which is then the brain area, we don't really know the elementary model then, right?
Right.
And if, for example, I discuss it with experts, if you look even at basic questions, for example, we used to think, for example, that neurons, in particular lamina, have distinguished role with regard to forward and top-down streams within brain areas. Now it turns out that there are at least 2 bottom-up streams which connect 2 columns in the lower and higher areas, and 2 top-down streams in the higher and lower kind of lamina. So it's as complicated.
Come on, man. Let's keep it simple here, Wolfgang. Let's not complicate things any more than they need to be, although they need to be. So yeah.
And then, for example, also another kind of more from the functional perspective, I think everybody agrees that brains must be good at predicting things, right? And so therefore, they must be all the time compare predictions with the actual ground truth that they're experiencing right now. And so there should be well-defined circuits which compare these 2 sources of information and then do something, subtract them or whatever. And as far as I know, and also as far as experts for this tell me, it's still not known really what neurons do this on which lamina.
Yeah.
So therefore, as far as I can tell, even for the most fundamental brain computations, we don't really know the players and the architectures for these computations then. And in that sense, I think we are pretty far behind then.
How do you think that relates to brain-machine interfaces and the potential for it? I ask because, I don't know how to really approach this without seeming negative, but so Elon Musk's company Neuralink just made a big, not announcement, but they just released something, and his notion is that, we'll just plug into the brain, it's a neural network, and we'll figure it out. But it struck me that, so Elon Musk, a very bright guy, gets things done. But all the things that he's done, Tesla, SpaceX, he's approached from first principles. And you can really do that in physics, for instance. You can, because the first principles are pretty established, right? So you can go back and figure out how to make a more efficient battery. You can make more efficient fuel for rocketing into space. But then I thought, well, what are the first principles for brains? Do we really have them? And I don't see them. I know that there are a lot of suggestions for first principles, but what you're saying is that those are missing still, the ground truth, let's say, if you can equate that with sort of first principles. And I'm wondering, is that going to hinder our ability to create brain-machine interfaces that are really effective? I know I'm taking a tangent here, but it made me think of it.
It's a good question. Yeah, I want to address this question, but at the same time, I want to complement my more kind of disappointment about understanding of really the computations in this basic circuitry is that there's a different perspective of kind of canonical cortical circuitry, that these are in the sense learning machines then.
Yeah.
And so therefore this suggests that it's a wrong question of simply asking just this circuitry, these neurons on this lamina, what do they compute, what they're made for. You could view them simply they're modules in a learning machine then. And I think this is really a view which has many arguments in favor of them. And then coming back to Maass and brain-machine interfaces, what one has had noticed then going back even to this experiments of Eberhard Fetz several decades ago, that it's not that the brain gives a certain output then. Whenever you engage a brain, take off signals and then engage the person in a closed loop, then where say you want now that this recorded brain signals should really now control a robot arm. Then as soon as this person is observing this and knows that this is the goal, the brain strives to make circuitry fit into this goal then, right?
So this is a learning principle.
Right. Adaptivity and learning is something which is really possibly an even more fundamental and important principle for understanding brain circuitry and brain function then. And then this gives us some hope then also, insofar as we also, as I mentioned before, we know, for example, from work, say from calcium imaging from the Tank Lab or Chris Harvey labs at Harvard, where they really see when a rodent learns something, a certain behavior, how does it change activity of neurons in a certain area. It was their PPT, posterior parietal cortex. And so therefore we have now really something in hand which we didn't have several decades ago, right? We see now how learning really changes circuitry on some level, and there's further work going in this direction then. I think what we are still missing is really the understanding on the kind of bottom-up level what happens in neurons and synapses during learning then. I think still there we're still up against simply fundamental experimental impediments that typically you have to do these experiments in slice then. In a slice, it's not a working system, it doesn't learn. And so therefore we're missing there a link in this, possibly in the end, the most fundamental link in this chain for understanding the organization of learning in the brain, really at the level of neurons and synapses. I think there the information is still very partial then.
That wraps up the first part of our conversation. Like I mentioned, I will release the second part in a few days. All right, goodbye for now. Brain Inspired is a production of me and you. You can support the show through Patreon for a microscopic $2 or $4 per month. Go to braininspired.co and find the red Patreon button there. Your contribution will help sustain and improve the show and prohibit any annoying advertisements like you hear on other shows. To get in touch with me, email paul@braininspired.co. The music you hear is by The New Year. Find them at thenewyear.net. Thanks for your support. See you next time.